equilibrium and ice tables. So ice stands for initial concentration, change in concentration, and concentration at equilibrium. And the ice tables are used to calculate the concentration at equilibrium given the K value and the initial concentration, or to use stoichiometry to determine the concentration of reactants and products at equilibrium. So you know that for a reactant, the concentration will decrease over time as it reaches the equilibrium point. And in an ice table, that's represented by negative Nx. The value of N depends on the coefficient of the reactant or product, the reagent. So if your coefficient was 2, it would be negative 2 for the reactant, and if it was 10, it would be negative 10x. For a product, the opposite is true, so the concentration will increase over time as it reaches equilibrium. And in an ice table, that's represented by plus Nx, and once again, the value of N depends on the coefficient of the product. The ice table measures the change in concentration for reactants and products using these variables in a chart format as shown in this generic ice table. So in the first row, we have our balanced chemical equation, A plus B is in equilibrium with C, where our lowercase letters A, B, and C are our coefficients. In the second row, we have the initial concentrations of all three, the reactants and the product is 0 since the reaction hasn't begun at the initial stage. The second row is the change in concentration, represented by negative Nx for the reactants and positive Nx for the product, so it's going to be negative Ax and negative Bx and plus Cx. And in the last row, we have the combination of the second and third, I plus C is going to be equal to E, and that's how we find the equilibrium concentration by adding the initial and either subtracting or adding the change in concentration. So now that we know what an ice table is, we can use that to solve this first question. So if 1.50 moles nitrogen gas and 3.50 moles of hydrogen gas are added to a 1-liter vessel and the reaction is allowed to reach equilibrium, the concentration of ammonia gas is equal to 0.540 moles per liter. What is the Kc value? So we can just fill out our ice table here. So we know that the initial concentrations are 1.50 moles per liter, 3.50 moles per liter, and 0 for the product. Then we know that the coefficient of N2 is just 1, so in the change row it's going to be negative x. And for hydrogen gas, since the coefficient is 3, it's going to be negative 3x. For ammonia, it's going to be plus 2x because the coefficient was 2. Now that we know that, we can add the rows I plus C to get our E row. So 1.50 minus x moles per liter, 3.50 minus 3x moles per liter, and we're already given in the problem that the concentration of ammonia is 0.540 moles per liter. From that last piece of information, we know that 0 plus 2x, I plus C is equal to E. So 0 plus 2x is equal to 0.540 moles per liter. If 2x is 0.540, then we can assume that x is equal to 0.270 moles per liter. Now that we know what x is, we can substitute that in the E rows for N2 and H2. So 1.50 minus 0.270 is equal to 1.23 with 3 significant figures. For H2, it would be 3.50 minus 3 times 0.270, which is 2.69 moles per liter. Now we know all the final concentrations at equilibrium of all our reagents, so we can use this to find our Kc value. We know that the Kc is equal to the concentration of the products raised to the coefficient of the product divided by the concentration of the reactants raised to the coefficient of the reactant. So in this case, it will be the concentration of NH3 squared divided by the concentration of N2 times the concentration of H2 cubed. That's going to be equal to 0.540 squared divided by 1.23 times 2.69 cubed. And that's equal to 0.0122 in 3 significant figures. So that's our final answer for the Kc value, and we got that by using the initial concentrations and one final concentration to determine the overall Kc and final concentrations at equilibrium. So the ice table can be used in many different ways, and one of them can be to determine the concentration of products given the K value and concentration of reactants. And to do this, there are 2 broad methods, either with quadratics or without quadratics. If we want to use quadratics, we use something called the quadratic formula, which is negative b plus or minus square root of b squared minus 4ac divided by 2a. Without quadratics, we can either solve the problem algebraically or using something called the 5% rule, which we'll go into later. So for this next question, let's use the quadratic formula to try to solve this. If the initial concentration of hydrogen gas is equal to 1.00 moles per liter and the initial concentration of I2 is 2.00 moles per liter, calculate the equilibrium concentration of H2I2 and its product, HI. The Kc is given to us as 50.5. So the first thing we want to do is to set up our balanced chemical equation. We already know that H2 and I2 are both diatomic molecules, but HI is not. So that's going to tell us that we have to make 2 of the HI. So H2 plus I2 is in equilibrium with 2 HI. In our initial row, we have the initial concentrations of H2 as 1.00 moles per liter, I2 as 2.00 moles per liter, and we know that our product is going to be 0. In the next row, we have the change in concentration. Since the coefficients of both H2 and I2 are 1, we have negative x and negative x. Since the coefficient of HI is 2, we have plus 2x. So in the E row, we just combine the I and C from the previous row. So we get 1 minus x, 2 minus x, and 2x. Since we weren't given any of the concentrations at the final point, we have to use the quadratic formula to determine the x value. We already know that Kc is products raised to its coefficient divided by reactants raised to their coefficients. That's going to be Hi squared divided by the concentration of H2 times the concentration of I2. We were given the Kc as 50.5. That's going to be equal to 2x squared divided by 1 minus x times 2 minus x. If we rearrange this by multiplying both sides by the denominator, we get 50.5 times 2 minus 3x plus x squared equals 4x squared. We can rearrange this once again and subtract 4x squared from both sides to get our final quadratic equation of 46.5x squared minus 151.5x plus 101.0 equals 0. We're going to use the quadratic formula here, which is negative b plus or minus the square root of b squared minus 4ac over 2a, and we get two answers, x equals either 2.32 or 0.935. Table that the concentration of H2 is equal to 1 minus x, and that's when we substitute in 0.935 for x, we get 1 minus 0.935, and that's equal to 0.0651 moles per liter for a concentration of hydrogen gas. For I2, we had 2 minus x. 2 minus x is going to be 2 minus 0.935, which is 1.065 moles per liter. For HI, it was going to be 2x, so 2 times 0.935 is 1.87. And notice how, so these are our final concentrations of each of the products and reactants at equilibrium, and that's what we were solving for. We did this using the Kc value and the initial concentration. So there's also something called the 5% rule. So using the 5% rule, if the change in concentration of reactants is less than 5%, then the change is considered negligible, and the reactant concentration equilibrium is equal to the initial concentration. In this case, the K value would be really, really small, and it would have almost no effect on the actual concentration of the reactants. So using that knowledge, we can answer question 3. N2 and O2 react to make NO. The Kc is equal to 2.1 times 10 to the negative 31st power. Just initially looking at the Kc value, we already know that it's going to be so small that we're going to use the 5% rule. Now going on, if the initial concentration of N2 is equal to 0.78 moles per liter and the initial concentration of O2 is equal to 0.21 moles per liter, let's determine the equilibrium concentration of NO. So once again, we're going to set up our ice table. The first thing we're going to do is to balance our equation. N2 plus O2 are in equilibrium with 2NO. Next, we're going to fill out the I row, which is our initial concentration, 0.78 moles per liter, 0.21 moles per liter, and 0. For our change row, since our coefficients of the reactants are 1, we'll have negative x, and for our product, we're going to have plus 2x. In the E row, we'll have 0.78 minus x, 0.21 minus x, and 2x. Since the equilibrium constant of Kc was so small, we can use the 5% rule and ignore the change in reactants because it was so little that it would have been negligible. That means that we can just simplify the E row for the reactants into just 0.78 and 0.21, ignoring the negative x of both of them. We'll keep the NO as 2x because it's the product. So now that we know that, we can find our Kc value. So Kc was going to be equal to products over reactants raised to their coefficients, so that's 2x squared divided by 0.78 times 0.21. If we solve for x, we get 9.3 times 10 to the negative 17 moles per liter. We know from our E row that the concentration of NO is equal to 2x. So that's going to be 2 times 9.3 times 10 to the negative 17, and that's 1.9 times 10 to the negative 16 moles per liter. And that's our final answer for the concentration of NO. We could also find the concentration of N2 and O2 if we hadn't used the 5% rule. We would just do the same thing that we did in the last problem using the quadratic formula or solve it algebraically. But the 5% rule is a lot easier because you'll notice that the numbers are so small, it doesn't really make a difference in this case. So thank you for watching this video. Feel free to comment if you have any questions, and I hope you guys enjoy your day. Thank you.